And a little reminder up there too, the ASUC lecture notes for Stat 21 in particular are at notes.berkeley.edu. And as I've said before, I think they're high quality, good product, and yeah, would be good for you. Okay. So I'm sort of in the middle of reviewing. I got through chapters 3 through 10 last time and just barely started chapter 11. So I think today I won't have time to do much more than review the rest, like review 11, 12, 13, 14, 15, 1, 2, and the summation handouts. Basically is my plan for today. If I have a little bit of time at the end, I'll do a little bit more probability. I'm going to do probability last anyway, so sort of naturally go into doing some examples if we have time. Okay, any questions, logistical questions, anything else going on? Okay, so review session, each GSI is having a review session, and most of them are during their regularly scheduled office hours, but they'll be in like a classroom or whatever. I haven't got the complete list, but hopefully by the end of the day I will have all the times and locations. I believe there will be one every day starting tomorrow, so every weekday, so Wednesday, Thursday, Friday, and Monday for the 4 GSIs. And it'd be nice just logistically if you can go to your own GSI's review session. It's not, I'll post them all on BSpace, so that if you can't make it, you can go to a different one. But I think it'll be pretty crowded if like everyone waits till Monday or something. So hopefully if you can make your own GSIs, then do that. They're not going to do, like I'm basically doing all the review. What they'll do there is solve problems. So mostly they'll answer questions. The only real reason why we call it a review is I think more people come if it's called review rather than office hours, and also that I think sometimes people feel like they need to have a question if they're going to go to office hours, whereas if it's a review, you're happy to go and just see what other people ask. So that's our intention is to have these have sort of slightly larger rooms reserved so that if people want to come and just watch what other people ask, and you can come even if you don't really have any questions necessarily. Okay? Student Learning Center, also a good resource, including that. And that's it, I guess. Yeah, so Thursday I'll be here to answer whatever questions, do examples. But today I think I'll probably not have much of a chance to answer a lot of questions anyway. Okay? Anything logistical? Anything? Yeah. Yeah, so her question is, on Thursday, does that mean I'm just sort of answering questions, like kind of like office hours? Well, I mean, it's going to be here, so presumably I think a lot of people will come, but I'm not going to like prepare a lecture, really, okay? If no one asks me any questions, I'll probably do some problems from the study guide and maybe some extra probability problems, stuff like that. So if you have questions, you can email me ahead of time, or if it's something like if you want me to, if you have like a specific question on a, like, how should I put this? If you want me to do a particular problem, you can just show up Thursday and ask me to do it. If you want me to like give an example of the regression effect or something like that, I can pretty much make up examples when you ask me, but you might get a better example if you email me ahead of time, and then I have a little bit of time to prepare an example that makes sense. Okay, so if you're going to ask me a general question on a topic, then maybe email me ahead of time. But like I say, if it's just like do this problem on the study guide, then you can just, I mean, if you want to email me, you can, but you can just wait until Thursday and ask me then. Okay? Any other questions? Okay, so I did chapter 10, and chapter 11, just set up again. So we're talking about the general situation where you have some scatter diagram, And I'll draw this for a football-shaped scatter diagram where we are making predictions along the regression line, okay? Neither one of those things has to be true in general, but that's usually what we do. Okay, so we could have something nonlinear. We could do something different than regression. For example, we could, one example I did in some detail is if we make all our predictions at the average of y, okay? So regression is one method of prediction. Guessing the average is another method of prediction. Whatever method of prediction we have our predicted values. Okay, so in this case, the predicted values are along the regression line. And we have actual values. The actual values are the dots, the points that could be anywhere in this picture. And I'll pick one here. And just point out that this, actually, I'm sorry, let me draw this a different way. Just want to do this. Let's do it this way. Predicted value is this value. And actual value is here. And the difference between them is what's called a prediction error, okay? Prediction error is equal to actual value, minus predicted value. So every single actual point in this picture has, its actual y value, its predicted y value along the regression line. And so we get a prediction error for every single point. And if we take the RMS of those, that's what's called the RMS error. Okay, and this is, in general, you can think of this as being defined, RMS error is defined this way for any prediction method. And any scatter diagram. Okay. So if you have so I've drawn this in particular for a football-shaped scatter diagram and the regression line. But like I say, in general, you can do this calculation, the RMS, the prediction errors, for any prediction method and any scatter diagram. Okay. However you want to determine your prediction method, whatever the scatter diagram looks like, it still has an RMS error. Okay, any questions about that setup? Okay, so for regression, the RMS error is equal to square root of 1 minus r squared times s dy. And for football-shaped scatter diagrams, we know these things. So I wrote these up last time, but I'll just remind you. The first thing is that it's linear with no outliers. The second is that x and y both follow the normal curve. And also normal in vertical strips. And finally, that the relationship is said to be homoscedastic. Which basically means that you have the same spread in each vertical strip. Okay, so 2 and 3 I've said in terms of vertical strips. Those things are also both true for horizontal strips, although we don't really ever use that. Okay, what we care about, well, the reason why we care about these things is to do normal approximation in vertical strips. Okay, so I guess first, any questions about this part? Okay, so the sort of typical vertical strip problem looks something like this. For all people with the same x value, something like what percent are above a given y value. Okay. So if you're trying to answer a question like that, what you're essentially doing is you're taking a, I guess I'm drawing a picture. So you're taking some particular x value, and you're predicting y. So you have this predicted y value, which the book and I sometimes refer to as the new average in this context. So that's the average y value corresponding to all these to all these people that have the same x value. And what do we know about the scores in this vertical strip? Well, we know their average. We know their spread is the same in every vertical strip, and that spread is, in fact, the RMS error. And we know they follow the normal curve. Okay, from this part. Normal curve in vertical strips. So I'll sort of draw this sideways. Okay, so if I kind of reproduce that curve, we can do this. The new average is here somewhere. And for a given y value, so suppose we have some y value here. And then if I want to find the percent above that, essentially I have to convert to standard units. So in standard units, this is 0. And this, to convert that into standard units, we take this y value, okay, whatever this y value is that's given to us, subtract off the new average, which we find by doing regression, and divide by the new SD, which is the RMS error. So this new SD is RMS error. Okay? So this all works as long as you have a football-shaped scatter diagram. So this is scatter diagram. Okay, so again, what the football shape tells us is it tells us that it's linear with no outliers. We need to know this in order for the regression method to actually tell us the average in this strip. So the first, number 1 over there, that it's linear with no outliers, it's what justifies using the new average here. The second part, normal in vertical strips, is what justifies the shape using the normal table. And the third thing, homoscedastic, is what justifies using the RMS error as the new SD here. Okay, so we're sort of using all those bits from football shaped in order to have this make any sense. So this has to be right, so it has to be linear with no outliers. This has to be right, so we have to get the normal curve in vertical strips. And then because it's homoscedastic, the RMS error works in every strip. Okay, so that's kind of a fairly typical, I don't know, variety of Chapter 11 problems to kind of do this thing where we look at all the people with the same x value and think about what percentage of them are above a given y value, below a given value, y value, whatever. The thing I think that makes some of the study guide problems harder than others is this part. Okay, finding the new average is just doing regression. right? Hopefully that part is, you're comfortable with by now. Calculating the new SD, RMS error calculation is pretty straightforward. Using the normal curve, pretty straightforward. The part that makes some of the problems harder than others, like I say, is this part. Because the questions sometimes are a little bit confusing. It's a little bit hard to see what y value you're actually comparing to. So when you see these problems, once you've determined that it's a vertical strip problem, and the way you do that is to recognize that we're talking about people with the same, everyone has the same value for one of the variables, that's x, the other variable is y, then most of the structure, it's sort of a fairly long problem, but most of the structure is fairly standard. Regression method gives you this, RMS error gives you this, and then this might be something like, what percentage of the people are above the 25th percentile of y values. So you need to figure out what the 25th percentile of y values is, plug it in there. Or it might be what percentage of them are above average. Okay, so then it's just the average of all the y values. So anyway, yeah, so some of the questions are a little bit weirder in finding this, but the basic structure is the same for those vertical strip problems. Okay, questions? Okay, so let me see. I think that gets us through chapter 11, everything I wanted to do. Yeah, okay. So let me do 12. So we didn't do that much of chapter 12. I guess what we did in chapter 12 is section 1 and about half of section 2. There are 3 sections. So we omitted the last part of section 2 and section 3 of chapter 12. So there's not that much. Most of it has to do with just finding the equation of the regression line, and then there's a little bit more about interpreting interpreting that equation and a few other bits. Okay, so the equation of the regression line. So I think it's important that you have the word predicted here. And it's important enough that I've decided that if you don't, I'll take off a point. You're sort of used to looking at the equation of a line in this way, y equals mx plus b. This sort of literally means that you can get the y values by taking the x values, multiplying by m, and adding b, right? So this suggests that the actual y values are on a line. And that's not true. What is true is that the predicted y values are on a line. So that's why I consider that word to be important. Yeah, what we're trying to do here is find the predicted values, and those are on a line. Okay, so what we do here is solve for m and b. So m is equal to r times the SD of y divided by the SD of x. Okay. The reason why that slope is what it is, just really quickly, if we imagine the point of averages being at the center there, and then imagine going up by 1 SD. So this point here is the average plus 1 SD for x. So 1 SDX. Then there's our line. Again, those are our predicted values. So what happens if we consider someone that's 1 SD above average for x, we predict that they would be r SDs above average for y. So this predicted value of y is going to be average plus r SD y. Okay, so the rise is r SD y. The run is 1 SD for x. So the slope of that line is r SD y over SDX. And I've suggested 2 different methods for finding b. The first method is what the book does is to predict y just using the regular old regression method. predict y when x equals 0. So this is basically saying, okay, if we just continue this line here, b is the y-intercept, so that's this distance. It's the predicted value of y when x equals b. What I've suggested is a little bit quicker. It's what I call point slope, which is to recognize that if x is at the average, then the predicted y value has to also be at the average. So if the average for x is x bar, the average for y is y bar, then we know that if we plugged in x bar, multiply by m, add b, that would give us the predicted y value. And if you're on the regression line, that predicted y value would be y bar. Okay? So if we know m, we've already found it, and we know x bar and we know y bar, we can solve for b. Okay, so you know, I don't care which one you do. I think this is a little bit quicker. The second one's a little bit quicker, and it's pretty easy to remember, right? Because it's just, rather than y equals mx plus b, it's y bar equals mx bar plus b, and then solve for b. And another reason I kind of like it is that it uses this idea that the point of averages is on the line. So it sort of reminds you of that. The book method is sort of nice, I think, because, or the reason why they do it is because it's sort of literally what you think of as the b value. It's the y-intercept, so it's the predicted y value when x equals 0. But it's a little bit longer, and I sort of, there's a sense in which I don't like it intuitively that much because x equals 0 may or may not be possible. It may or may not make any sense. You might be talking about heights or something, and then the math makes sense, it works, but it doesn't really make sense to predict someone's weight whose height is 0. So. Okay, so questions about that? Sort of the nuts and bolts of chapter 12 to find the equation of the regression line. And just a couple of quick facts. The regression line has the smallest RMS error of any line. And that's basically why we use the regression line, is that if we used any other line to make our predictions, it would have it would have a larger RMS error. RMS error intuitively measures the typical distance from the regression line. So having a small RMS error is basically telling us that the predicted values are generally pretty close to the actual values. Excuse me. Okay, so that's why we do regression, essentially. So the book kind of re-emphasizes in this section that correlation does not imply causation. So in general, don't use slope of regression line to determine the effect of a change in x. Okay. So one just quick example I used for this in class was if I ate 5 pounds of ice cream, you shouldn't expect me to get taller. So changing, even though there's a positive correlation between height and weight, if my weight goes up, it doesn't necessarily mean my height's going to go up. Okay. So there's not, in general, a causal relationship. If the data are from a well-run experiment, we can determine causal relationship. Okay, so what I mean by well-run experiment is a little bit tricky. A lot of times people do experiments and they think they've got something, but they made some mistake that they didn't see or figure out, and it messes up their results. Okay, and that's really the subject of chapters 1 and 2. So that's kind of why why I taught in this order, was to do chapter 12 now, and then go and talk about chapters 1 and 2 in this context. Okay, so that basically wraps up chapter 12. Although I will talk about this last part in the context of chapters 1 and 2. So, questions? Okay. So really, mostly what I want you to get out of chapters 1 and 2, I want you to understand the words used in those chapters. And I don't care so much about you understanding the examples. Well, I shouldn't say that. I don't care about you knowing the details of the examples. I would like you to understand the concepts behind the examples, but the specific examples I don't really care about. So I'm just going to say them. The definitions you can look through your notes or look in the book for. I'm just going to write down the words and just briefly talk about them. So there's an observational study, there's an experiment. I guess the book usually refers to this as a controlled experiment to make it clear that in an observational study, you're basically observing things. You don't get to control what people do. You just watch whatever they happen to do and try to draw some conclusions about the data just based on your observations, basically. Okay, so that's not so great. The main problem with observational studies is that there may be confounding factors, and there may be confounding factors that you don't think of. So confounding factors are variables that are associated with both the treatment and control. Sorry, both the treatment and the response. So in the context of these observational studies and controlled experiments, whatever the treatment is. The treatment could be a drug that's supposed to help you reduce your risk of heart disease, reduce your risk of polio, if it's a vaccine or something like that. Could be something bad. The treatment might be smoking, or drinking alcohol, or drinking coffee, or whatever. And the response is whatever it is you're measuring. So you might be measuring like the percentage of people that get cancer, or that die, or they get heart disease, or whatever. So a confounding factor is something that's associated with both. So one example I gave before is if you're interested in the relationship between drinking coffee and lung cancer, confounding factor would be smoking. That smoking is associated with both drinking coffee and with getting lung cancer. So it sort of confuses or confounds the relationship between coffee and cancer, lung cancer. Okay, so that's a problem with observational studies. It can be a problem with controlled experiments if they're not run so well. So the polio example I did in lecture, the first experiment they did, I wouldn't say that experiment was well run. It was controlled, but they had a couple problems. So the confounding factor that's the main problem in that example was consent. That the group of people they gave the vaccine to were all people that consented to get the vaccine. Of course, they have to be, right? But what you'd like to do is you'd like to compare them to a group that also consented, rather than comparing them to non-consenters. So the good experiment, the well-run experiment for polio, the second experiment I talked about, took all the consenters in one big group and then randomly divided them into two parts. One half got the vaccine, one half got a placebo. So now we're comparing people that all are, sort of volunteers. They all agreed to be in the study, so they don't. There's not this problem that consent is associated with the treatment, right? Everyone who got the treatment, everyone who didn't get the treatment that we're comparing them to, all those people consented. Okay. All right, so that's little bit about confounding factors and how it relates to both these cases. Yeah, so I guess I didn't quite say control experiment. The investigators or experimenters control who gets the treatment, who doesn't get the treatment. Okay, questions about those three? Yeah.
When you say controlled experiment, does that imply that a control is used?
The question is, when I say controlled experiment, does that imply that a control is used? No, it's a different use of the word control. So controlled here means that they control who's in the treatment group and who's in the control group, okay? So there has to be a group, there has to be a control group, but you could have a control group without having a controlled experiment. Does that make sense? So in an observational study, you can still consider comparing the smokers to the non-smokers, and you would think of the smokers as being the treatment group and the non-smokers as being the control group, even though it's not an experiment. Does that make sense? Yeah. Okay. Good. Any other questions, thoughts? Okay. So that's the sort of main ones. There's some other ones along the way. There's the idea of double blind. So double blind means two kinds of blindness. The blind just means that you don't know which group you're in. So double blind, the first kind is subject blind, meaning the subjects themselves don't know what group they're in. So in the polio vaccine example, in the good experiment, they did that. They gave the control group a placebo, which was an injection that was indistinguishable from the actual polio injection, so that the people didn't know the kids didn't know if they got the vaccine or not. And I mentioned when I talked about it, that's sort of more important for some experiments and less important for others. I think if they were looking at an AIDS vaccine, it's really important that it's subject blind. It's really important that the people don't have any idea whether or not they've gotten a real vaccine or not, because if they know they've gotten a vaccine, they may tend to engage in more risky forms of behavior. And I'm sure you all know what those kinds of behaviors are. So for that reason, you have this problem. The knowledge that they have a vaccine, that they've gotten a vaccine, may change their behavior. So may have this higher risk for them. For something like polio, probably not as big of a deal. The difference between a kid who engages in sort of risky behavior with respect to polio and doesn't is probably relatively minor. We're talking about things like going to a public swimming pool or eating dirt, things like that. And probably there's not a huge difference between the behavior of a kid that knows that he's vaccinated and a kid that doesn't. Yeah, so it's probably not as big of a deal. But you might as well do it. It's not too bad for a vaccine to just go ahead and give a placebo to the control group. Obviously, for something like surgery, you can't really have placebo surgery. So yeah, okay, so that's sort of a bit about subject blindness. The other kind of blindness, the evaluator blindness or investigator blindness, means that the person who is deciding what the response, like sort of measuring the response, doesn't know what group the subject's in. So whoever is giving the polio diagnosis in that example doesn't know if the kid's vaccinated or not. Again, maybe more important for some studies than others. Probably polio diagnosis is relatively objective. Certainly if the response is something like whether or not the person's alive or dead, that's pretty objective. It doesn't really matter if the person that's trying to decide if you're alive or not knows whether or not you're vaccinated. But if it's a fairly subjective response, like you feel better today or something like that, the doctor or whoever is evaluating you may be able to consciously or unconsciously kind of bias your results a little bit. They may be really happy and optimistic when they talk to the test subjects that got the vaccine or got the treatment, and they may be sort of unhappy having to deal with the ones that are in the control group or something like that. So they may slightly affect the responses if it's, like I say, if it's subjective. Okay, so that's that. Just say randomization is often used in control experiments in order to ensure that there's no systematic difference between the two groups. If I were testing the polio vaccine or something like that in the class, and I just said, okay, this half of the class gets the polio vaccine and this half of the class doesn't, I mean, it seems pretty random, it seems pretty good, but you never know. There might be like an air vent over there that's linked to some hazardous waste place, or I don't know, something that affects one half of the room differently than the other. So by doing things randomly, you ensure that there's no kind of systematic way that creeps into your experiment that makes the groups different. So I said before, I'll repeat again, what I said when I originally lectured on this. Ideally, what you're trying to go for in a controlled experiment is that there are no differences between the treatment group and the control group except for the treatment. Okay? And again, if you do things randomly, there may be slight random fluctuations, so slightly, you know, one group may be slightly healthier or sicker randomly. But any differences should be minor and are well studied by statisticians. Okay? So statisticians are and we'll do this later in the class. Statisticians are good at dealing with these kind of random things. But the systematic things, anything that comes in systematically, you can't really know exactly how big of an effect it is. Okay. I think that's all I wanted to say about 1 and 2. Yeah, so again, there's this idea that correlation does not imply causation, confounding factors are a problem, all this. Okay, so just to connect back to the chapter 12 part, if we have a well-run experiment, and essentially what I mean by that is that there's no systematic difference between the treatment group and the control group, then it makes sense to use the regression line to determine the effect of changes of y and on changes of x. So if this is a picture where the x-axis is like dosage of a diet pill, and the y-axis is well, maybe that's not such a good example just because there'd be negative correlation, I guess. Hopefully more diet pill means your weight goes down. So let's say it's a weight gain pill. There's a pill that you could take to gain weight if you wanted to. And if we control the dosages carefully and have different dosages along the x-axis here, and it's in a well-run experiment, the subjects don't know how much of a dosage they're getting, and all this stuff is done right, then we can determine that, in fact, giving that much of the pill or of whatever active ingredient it has should, on average, make you gain whatever the regression line would say that you would gain. If, however, the data comes from an observational study and you just sort of like observe how many diet pills people take and you don't control it, then all you can determine is that, or I guess, sorry, weight gain pills. All you can determine is that the people that take more of the pills tend to be heavier, and you don't know why. It might be the people that take more of the pills watch more TV and sit around on the couch more. The people that take less of the pills, exercise more, eat better, whatever. Okay? So because there are possible confounding factors, observational study, you couldn't use the regression line to determine the effect of changes of x on y. Okay? Any questions about any of that? Okay, so that's the end of, I don't know, sort of the data part of the class. The things I still want to talk about today are the summation stuff and the probability stuff. So that's all sort of a little bit separate. The summation does talk about descriptive statistics, but it's basically just the math. All right. So actually, that's a pretty good time for a break. So I'll take a little break, and then I'll do the summation and probability. Okay, why don't I get started again? Okay, so I think probably, well, so what I'm going to do today is I'm going to talk through the handouts a little bit and talk about sort of the typical kinds of problems you might see for summation. But I think I won't have time to do that many examples of either summation or probability. So I'll do that, and then I'll review probability. And then I think those are probably the two areas where people will want me to do problems the most on Thursday, the summation part and the probability part. So yeah, so we'll end up seeing more examples of that on Thursday. So let me just go through the I don't know, my intuition, I guess, behind what's going on with summation. So I think a lot of what people find hard about summation is just kind of manipulating the summation stuff. So I just want to kind of remind you of the formulas. This x bar is equal to sum of the xi's over n. Okay, so basically the summation is just adding up all the values, the xi's are the actual values, adding up all the xi's divided by how many there are. That gives you the average. Okay, the standard deviation, the book formula is to take the RMS of the deviations from average, and in summation notation, what that means basically is we take deviations from average. So these xi's are actual values, subtract off the average, so that's a deviation from average, and then we want to square them, right? RMS, right? So we're taking these, and the s means that we square them. Taking the mean means that we add them all up and divide by how many there are. And then the r is square root. So again, RMS of the deviations from average means square root of the mean. So sum divided by n is the mean of the squared deviations from average. So that's sort of the way you might think of the book formula being translated into summation notation. There's another formula I think is generally a little bit easier. Okay, and if you want to sort of read this in English, this is saying take the square root of average of the squared values minus the square of the average. Okay, so that's that formula, and like I said, I think that's a little bit easier for most computations. And on the other handout is R, and I'll just write it down here along with the average and the SD. Again, there are two formulas, and the book way of thinking about the correlation is to convert x and y to standard units, take the products of those standard units, and then take the mean of the products, the average of the products. So what does the product look like in standard units? Well, converting x into standard units means that we subtract off the average, divide by the SD, SDX, and then do the same thing to y. Take a yi, subtract off the average, divide by the SD of y. So that's x in standard units, y in standard units. Take the products, and then take the mean. So I'm just going to, well, I'll do it this way. I equals 1 to n, and then divide by n. Okay? So again, the book way of thinking about correlation is to take the x values in standard units, take the y values in standard units, take the products, and then take the average of the products. Okay, so that's the book way. Again, there's, I think, a slightly easier formula to calculate, which is this. Take the average of the products of the x's and the y's themselves, not the standard units, but just take the average of the products of x and y. So this is xi, yi, product, average. Subtract the product of the averages and divide by the product of the SDs. Okay? So like I said, I think it's a little bit easier. All right. Any questions about the formulas? Okay, so then properties that, or sorry, problems that you might see. Mostly involve taking some original list of numbers and changing it in some way, and then, so you generally know the summary statistics somehow for the original list of numbers, and then you do something to that list, and then you want to find the summary statistics for the new list. Okay, so the idea there, so many summation problems. Have this kind of general idea that you know summary statistics or something similar. Like somehow you know something you can write down in summation notation. It might not be exactly that formula, but maybe you know the RMS of the x values, or you know I don't know. So you know something somehow about the you know the RMS of the deviations from 5 rather than the RMS of the deviations from the average. So somehow you can write down something you know in summation notation, and then you play with it, and then you want the new. Okay, sorry. Let me change list in some way. And then you find the new summary statistics. So the most common change that I've done in here for your homework, for examples I've done in lecture, is to have some of the people go away or add more in, right? So the idea in those kinds of problems is that if you know the summary statistics, well, I'll do it for x bar first. If you know x bar and you know how many people there are, then you know what the total of all the values is. And if some of the people leave, or if more people get there, well, somehow you should be able to figure out what the sum of all the values is once that happens. So so figure out what change happens to that sum of the values, and then divide by possibly a different n, if a different number of people are there now, and then find the new average. Same basic idea is true for both of these. If you know the SD and you know the average, those are the summary statistics for x, then you can find this. You can find the average of the squares, and if you know n, you can find the sum of the squares, just the top part. And then if you add more people in, or some people leave, or whatever, if you can find the sum of the squares for the people that leave or for the new people that are added in, then that tells you what you have to do to this. You change this in some way, add in more squared values, or take away some of the squared values. N changes. Perhaps the average changes also, and then you can find the new standard deviation. Okay, so just sort of big picture, that's what's going on for a lot of those problems. So finally, for R, same basic idea. If you know the averages, you know the SDs, you know R, maybe you know N, you can find the sum of the products, and if there are new people or some people leave or whatever, that changes in some way. Maybe that changes N, maybe that changes the averages, maybe that changes the SDs, but somehow you can kind of sort through it all and figure out what R has to change to. Okay, so that's the basic idea. And on the first handout, I described that as finding the SD of a long list. This idea that if you add more people on, you should be able to find the average in the SD for the longer list, the bigger group. Okay, so yes, you'll see a bunch of problems in the study guide, both mine and Purvis's, that get at that idea, that sort of core idea, in a variety of different ways. Okay, but somehow this basic idea is in there, that you should be able to write down what you know in summation notation, and then figure out what you need to know, and kind of go from one to the other. Okay? So somehow, if you're after the standard deviation, you better be able to figure out what the sum of the squares is or the average of the squares somehow. If you're after the correlation, this typically is the hardest part, is to find the sum of the products or the average of the products based on whatever it is you happen to know already. Okay, questions on any of that? Okay, so there's a little bit more on the handouts about the properties. You can look at that yourself. I don't think there's much point in me going over those again. You don't need to know, if you remember for the summation handout for the average and the SD, there's a formula for the sum of the first n integers, 1 plus 2 plus 3 plus 4 plus 5 up to n. There's this formula for that. You don't need to know that. And there's also a formula for the sum of the first n squared integers, 1 squared plus 2 squared plus 3 squared plus 4 squared up to n squared. You don't need to know that. Okay. So that's, I think, all I want to say about the summation handouts. Unless anyone has any questions or wants me to talk any more about it. Okay, so then probability. Okay. So I'll sort of review this all at once. Chapters 13 through 15 and the probability handout. Oops, probability. So the handout actually gives you, I think, a pretty good outline of what is in those chapters, although it's in a different notation. But basically we have these things. I'll just write them down really quick. Equally likely outcomes. If all outcomes are equally likely, the probability of any event can be written as the number of ways the event happens divided by the total number of possible outcomes. Okay, so that maybe seems fairly straightforward, but you can solve fairly complicated problems with this. For example, if you have 2 die rolls, you can make a grid, the 6x6 grid, and just figure out whatever event it is you want by counting 36 possible outcomes in that grid, and then figure out just where is it that my event occurs. Okay, so that's something you might consider for problems like that. There are some problems in the book where you have like 2 draws as some other way. So you might have like a box with the numbers 1, 2, 3, 4 in it, box with 1, 2, 3, 4, 5. This is an example in the book like that. We have 1 draw from the 1, 2, 3, 4, 1 draw from the 1, 2, 3, 4, 5. If you make a 4x5 grid, then again, you can sort of look at the 20 possible outcomes and just figure out, okay, where is the event that I want, count how many ways it happens, divide by the total number of possible outcomes. So there's some problems like that, especially you sort of notice these problems with 2 draws or 2 something. You can make these grids, and that often simplifies your life. Okay, so then complements. The book usually refers to as opposites, but I kind of prefer the word complement. Essentially says the probability of an event is 1 minus the probability of its complement. If you want to think about what a picture for that looks like, we have event A in there. Event A complement is everything outside of A. A complement basically means that event A doesn't happen. And the Venn diagram represents everything that could happen. So the total area is 1. And so if you want to find the area of the circle A, then you can take 1, the total, and subtract the probability of A complement. Okay? So that's sort of goes both ways. The probability of A complement is 1 minus the probability of A. So if you want to do it backwards, you can do it backwards too. And I make this comment on the handout that a couple of things that have relatively simple complements, problems where you see at least 1. The complement of at least 1 is none. So sometimes it's easier to deal with the chance that something never happens rather than the chance that it happens at least once. And not all also has a fairly simple complement. The complement of not all is all. So that just means that either, like, if you draw from a deck of cards, either not all the cards are diamonds or all the cards are diamonds. Okay? So those two things are complements. And like I say, again, the complement of that is often easier. Not all, there are different ways that you could get not all the cards to be diamonds in like 5 draws from a deck or something like that. You could have 0, 1, 2, 3, or 4 diamonds, and it would be not all diamonds. But there's only one way to get all diamonds. They're all diamonds. Okay? So any questions about complements? Okay, so then I guess I'll erase that there. Okay, so multiplication rule. Multiplication rule says that the probability of A and B is equal to the probability of A times the probability of B given A. This is the conditional probability. So this is that vertical line means given. So that conditional probability I think of as well, a couple ways you can think of it. One way is to imagine that you're in a universe where you know that event A happens. It's already happened. It's done. Okay. Now you just have to figure out, well, in that universe, what's the chance that event B happens? Another way to think about it is think about it in terms of long-run proportions. You could think about like everyone in the class, and of the people in the class, some proportion of them maybe have event A happen, and of those, what proportion of the people that have A happen also manage to have B happen? Okay, so then you think just confine yourself to the people that had event A happen, and think about the proportion of them that you would expect to have B happen. Okay, so that's that. Sometimes I think of this as overcoming successive hurdles. So one hurdle is to have event A happen, and then once you've gotten past that hurdle, then you think about whether or not B happened and what the chance is that B would happen. Okay, so there's a special case of that for independent events. So independence. So A and B independent means the probability of B given A equals the probability of B. And there are a few different ways to write it. That's, I think, how we would normally define it. But if you wanted to, you could also define it as this, for example. Okay, so I sort of think about independence in English sort of like this. That's basically why I'm writing it down, is that this is saying that whether the chance that B happens is the same whether A happens or whether A doesn't happen. So this represents, like, in a universe where event A happens, what's the chance of B? This universe, this probability represents in a universe where A doesn't happen, what's the probability of B? And if those two are the same, then it doesn't matter whether or not A happens. So that's one way to think about it. So if you ever want to check whether or not two events are independent, you can check it this way, you can check it this way, or you can use a special case of the multiplication rule. Which says that if A and B are independent, the probability of A and B is equal to the probability of A times the probability of B. Okay? And that's true if there are more than 2 events too. Like if you have like 5 die rolls, you want to find the chance that they're all 6s. You just go ahead and multiply them all out. First one's a 6, second one's a 6, third one's a 6, fourth one's a 6, fifth one's a 6. They're all independent. We want to find the chance that all of them happen. So it's like A and B and C and D and E. So multiply them all out. Okay, and you can kind of see that that makes sense, that the general form of the multiplication rule has probability of A times the probability of B given A. Well, if the probability of B given A is the same as probability of B, that's what independence says, then this is probability of B, and we get the special case. So along the same lines, oops, I guess I didn't spell independence right here. Independence. So if this is true, if the probability of A and B is actually equal to the probability of A times the probability of B, then we know they're independent. So that works both ways. If they're independent, then this is true. If this is true, then they're independent. Okay, questions about the multiplication rule? Yeah?
So that's conditional probability, right?
This right here is a conditional probability. Yeah, it's the probability of one event given another event. So if it's given something else, that means it's conditional. Is that what your question was?
So that's like the probability, like for cars, like 13 out of 52 multiplied by 12 out of 51.
Yeah. So the probability that if you let event A be standard deck of cards, I draw 2 cards. If event A is the first card in the deck is a spade, event B is the second card in the deck is a spade, the chance that A and B both happen is the chance the first one's an ace, first one's a spade, times the probability the second one's a spade given the first one's a spade. So it'd be 13 out of 52 and then 12 out of 51, because if the first one's a spade, that means there are 51 cards left and 12 of them are aces. Spades. 12 of them are spades. Okay? Any other questions? Yeah. So if I just asked you for the probability of B, the probability of the second card is a spade, that's not the same as this. That's not 12 out of 51, right? That's going to be 13 out of 52, because I don't tell you anything about the first card. If you don't know anything about what the first card is, then there are 52 cards that could come up second, right? There's still 52 cards that are possibilities to be the second card, and 13 of them are spades. Yeah?
If PA equals to 0, is it also true that if PA and B equals to PA times PB, then A and B?
Yes. The question is, if the probability of A is 0, is this still true? And the answer is yes. If any event that has probability 0 is technically it's independent of every other event. Meaning, so you can look at that 2 different ways. One way you can look at that is that if you look at this multiplication rule, well, probability of A is 0, so the right-hand side is 0. If the probability of A is 0, then A and B can never happen. If A can never happen, then certainly A and B can never happen, so this is going to be 0 also. So A and B are going to be independent in that case. If you want to think about it in terms of these, probability of B given A is a little bit silly because A never happens. But if you imagine that, if you just imagine an impossible universe in which A did happen, you can still imagine whether or not, or what you can imagine what the chance of B would be. So this still makes sense as a probability, and it might or might not be the same as the probability of B. If they are the same, then they're independent. Okay? Does that help? One way you might think of it is it might be easier to think about this, okay, which is equivalent. If A has probability 0, A complement has probability 1. And so A complement always happens. And certainly if A complement, since A complement always happens, the probability of B given A complement must be equal to the probability of B, right? Because telling you that, giving you that A complement happens doesn't really tell you anything. Well, you knew it was going to happen. It had probability 1. It's sort of silly to add that on. So certainly that probability should be the same as the probability of B. So if B and A complement are the same, if B and A complement are independent, then B and A must also be independent. Okay? All right. So let's do addition rule. Addition rule says the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And the way I usually think about why that's true is to think about this picture. If you want to find the probability of A or B, that's anywhere in this region where the two circles are. And if I want to find that area, I could take the area of A, add on the area of B, and that'd be too much, right? I'd be counting the section in the middle twice. That section in the middle is where A and B both happen. So by subtracting probability of A and B, I avoid double counting. So I still count everything in this middle section. It's just that I count it only once. I don't count it twice. So that's why you have to subtract this. It's not that you don't want to include it. It's just that you don't want to include it twice. Okay. Questions about that addition rule? Okay, so people often ask me, how do I know when I should add and when I should multiply? And basically, what you're looking for is some way to, you have some word problem, and you want to find some way of rewording the problem so that you're talking about the probability of one event and another event, or like both events happen, or something like that. Or you want to try to reword the problem in such a way that you can think about it as the probability that one of the events happens or the other event happens. So it's not necessary that both of them happen. It's just necessary that either one happens or the other one happens, possibly both. Okay? So if you can do that, if you can reword it to include the word A or and in your problem, then that tells you if you should add or multiply. It's not because your decision of whether or not to add or multiply should not be based on like whether or not the events are independent or something like that. Independence gives you a special case of the multiplication rule, but it doesn't tell you whether or not you should use the multiplication rule. Okay? So then the last little bit here, mutually exclusive, also doesn't tell you which rule to use. If you've decided to use the addition rule because of this or in the problem you're looking at, or you've sort of somehow reworded it to include the word or, if you've decided to use the addition rule, then mutually exclusive gives you a special case. Mutually exclusive means the two events can't both happen. Or they don't overlap, or something like that. Mathematically, this means the probability of A and B is equal to 0. For a picture, it looks like this. Okay? You have these two circles, they don't overlap. Okay, so that's what mutually exclusive means. And again, you have this special case. Special case of addition rule when A and B are mutually exclusive. Okay? And this special case says that the probability of A or B is equal to the probability of A plus the probability of B. So you could happily go through your life doing probability problems, if that would be happy, without really knowing this, without really knowing the special case. Because if you go ahead and try to use the regular form of the addition rule, you find the probability of A, you find the probability of B. Then when you get to this point of finding the probability of A and B, well then hopefully you realize, oh, that's 0. So then you sort of get to the special case of the addition rule without realizing it. Okay? So if you're just solving problems, you don't really need to do this. But it does make your life a little bit easier and a little bit faster, I think, if you recognize from the beginning, okay, we have this situation, I can just add them. And it'll work for more than 2 events also. If I have A, B, and C, and they're all mutually exclusive, probability of A or B or C, you can just add them. Okay? All right, questions about that? Okay, so let me just do the binomial quick. I guess I'll go ahead and erase these now, since it's pretty much the end of class. Lecture notes at notes.berkeley.edu. It's not too late. You can still get them. And SLC study group tomorrow, or review tomorrow, 7 to 9 in 2040 VLSB, which I guess is either that way or that way. Is it that way? Not sure. It's one of these 2 rooms. I guess it is that way, huh? Okay, it's next door anyway. Okay, so last thing for probability is the binomial formula. So the binomial formula is pretty specific. It's used when you have a situation where you have n independent trials. Each with probability p of success. And when I say success, it's something like if you're flipping coins, it might be getting heads. If you're rolling dice, it might be rolling a 6, whatever. Each with probability p of success. So if you're in this situation, then the probability of k successes you could write like this. Okay, so the way I think about this formula is that this part, the p to the k times the 1 minus p to the n minus k, this is the probability of a specific sequence. It's the probability of one sequence. So specifically, I'm talking about like success, 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 k times, and then failure, 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 however many failures, all in a row. N minus k times. Okay? So this is the p to the k. P, it's like p times p times p times p times p times p, 1 minus p, 1 minus p, 1 minus p, 1 minus p. Just multiply it all out. This is the probability of that particular sequence. And then this thing out in front tells you that, well, it didn't have to happen in that order. You could have mixed up these successes and failures, and this is the number of ways you could have made it in a different order. So a number of different orders you could have written it in. All right, so you can use that for problems like roll a fair die, say 10 times, and find the chance of getting exactly 3 6s. Okay? So n, that's the number of trials. It's 10. They're all independent die rolls. Okay, so it sort of fits in that framework. It's a fair die. Each roll has a 1/6 probability of getting a 6. So p is 1/6. And k is the number of successes you get. So you have 3 successes. And then you can just plug it in. So n factorial over k factorial, n minus k factorial, and then 1/6 the third, 5 6, that's 1 minus p to the 10 minus 3, or 10, this to the 7. Okay, so it's like 3 6s in a row, 7 non-6s in a row, this many different orders I could have put it in. Okay. All right, so that's that. And Thursday I'll do examples. So again, feel free to email me if you have any particular stuff you want me to talk about more or do examples of. Okay? Bye.